On Tuesday, we started doing optimization problems, and we did this problem, if you recall, with the gas and heating oil. And we found this little triangle area right here to be what we call our feasible region. So where before, when we were just graphing systems of inequalities, we called that our solution set. Now we're using the term feasible region. So we can then take this a step further and find our optimal solutions. Okay, so before we were just saying the solution is in the feasible region, and now we're going to find possible solutions. So you remember that our triangle looked something like this. Okay, and it was filled in like this, and our points on the graph were 3, 6, 0, 6, and these are our coordinates, and 0, sorry. Let me just redraw that. Okay, so 3, 6, 0, 6, and 0, 0. And so this is our feasible region within this pink triangle. And if we look at the 3 vertices, so basically where the lines of the triangle meet. Okay, so here 2 lines meet at this point, 2 lines meet at that point, and 2 lines meet at that point. And they're filled in because the inequalities were both included. And so if we look at our points on the HG graph, okay, so instead of x, y, we had h and g. There's 0, 6, 0, 0, and 3, 6. And then we want to, because the whole point of the question was to maximize revenue. So if we look at these, which one would minimize the revenue? And it would be, if you were thinking 0, 0, because that's the lowest, you're correct. So that would minimize the revenue. And then which one do you think would maximize? So we're going to go with the highest one, 3, 6. But then we can look at all 3 points and actually test to see which is the minimum and which is the maximum. And we have to use our objective function. Now that was the equation that we wrote for revenue, not an inequality, an equation. So it was 1.10 because that was the price for gas, or that they got when they sold gas, and 1.75 for when they sold heating oil. And again, these are ordered HG instead of XY. And all we have to do is fill it in. So if we go R equals 1.10 times 6 million, because remember that we were in millions, plus 1.75 times 0. And that would give us a revenue of, in dollars, since revenue is in dollars, 6.6 million. Okay, so let's try 0, 0. So R equals 1.10 times 0 plus 1, 1.75 times 0. So R will be 0. And then here R equals 1.10 times 6 million plus 1.75 times 3 million. And this revenue will give us 11,250,000. So if we look at the values, 6.6 million, 0, and over 11 million, we'll see that this is our, in fact, just like we predicted, this is our minimum solution. And this is our maximum solution. Okay, and of course, like we put here for millions, that G and H are in millions of liters. And we filled this out on our graph if you go look back. Okay, so now that we've substituted in, we can verify that these points fit within the constraints. So remember that the constraints were that at least 2 liters of gas were produced for each liter of oil, and that the refinery can produce no more than 9 million liters of heating oil and no more than 6 million liters of gas each day. So we write in our inequalities that we came up with. H is less than or equal to 9 million, and G is less than or equal to 6 million. And we just fill it in. So we're going to use our maximum. Okay, so to get revenue equals 11,250,000, and this, we get this maximum using 3 million and 6 million. Remember that this is our H and our G. So we fill in our 6 million greater than or equal to 2 times 3 million. And let's see, so we'd have 6 million is greater than or equal to 6 million. Is that true? Is 6 million greater than or equal to 6 million? Yes, it's true. Okay, so far so good. Let's try that heating oil has to be less than 9 million. So heating oil is H, so we have 3 million is less than or equal to 9 million. When we look at it, is 3 million less than or equal to 9 million? It is, so that's true. And then we test our last one. So G is 6 million. So we have 6 million less than or equal to 6 million. Is 6 million less than or equal to 6 million? It is, so that's true. So our maximum value is verified. We've just verified it with each of the inequalities. Now let's verify our minimum, and that was for R is 0 with the point 0, 0. And again, that's H and G. So again, we test our same inequalities, and this is what we came up with in the very beginning of the question. And you can go back and check those out if you don't quite remember them. So 0 is greater than or equal to 2 times 0. 0 is greater than or equal to 0. Is that true? It is. 0 is less than or equal to 9 million. Is 0 less than or equal to 9 million? It is. And then 0 is less than or equal to 6 million. Is that true? Yes. So both our minimums and our maximum have been verified. So we know that those are in fact the solutions. So in summary, the optimal solutions, so that would be the maximum and the minimum, because to optimize, you either want to maximize or minimize a value, to the objective function. And remember, this is our equation, okay, not an inequality, an equation. So like the revenue or the cost are usually found at the vertices of the feasible region. Okay, so if you had a triangle like this, here's your vertices. Okay, if one or more of the intersecting points is not included, open point, then the solution will be nearby. So if instead of points like that, I had a circle here and like that, and say this was my maximum, just in theory, then I can actually use that hollow point. So my solution would be somewhere nearby, maybe somewhere up there, okay? And we can determine the optimal solutions by testing each point with the objective function. So what you would do is choose points near the open dot and then test them. And then, again, verify them using the constraints. And the constraints are some of the inequalities. This would be inequalities. Okay, so with the gas, it would be that they can only produce so much gas a day. With that toy car question, it would be that they can, what was the toy car question? You know, that they had to produce a limited number of each type of car a day because of this limit of supplies. And that they had to make at least 70 cars. So let's look at, if you flip open your textbook to page 334, question 1, we'll just go over 2 examples. So we have our objective function. And it's t equals 2x plus 5y. Okay? And notice that it is shaded because we're given the constraints that the restrictions that x is all real numbers and y is all real numbers. And we're given the points, and you can see them on the graph. So if this is your graph here, it looks something like this. And you have hollow dots up at the corners there, and this vertice is a solid dot. And you'll see that those points are, so points x, so if they're written like xy, are -4, 3, 11, 3, and -4, -12. Okay, and then we look for our maximum and our minimum. And so here is our maximum, 11, 3, because that's the maximum value, and our minimum value is -4, -12. And we also have to say that this guy is not included because it's a hollow dot, like we drew up here. So here's -4 and 3, and here's -4, -12. So those are both hollow, so they're not included. And this guy is not included. Okay, so for 11.3, we say that's our maximum, and it's a solid dot. So we can just say right away that 11.3 will give us the maximum solution. And the restraints or the constraints are listed there, so you can always test it to verify. However, the minimum right here is not included. So this is where we'd have to say near -4, -12 will give the minimum solution. So the minimum solution in this case is not minimum. So the minimum solution in this case is not -4, -12, it's somewhere nearby. Okay, and because this is all real numbers, it could be a fraction or a decimal, because it could be anywhere in that feasible region. So our maximum is 11.3. That's our maximum solution. Our minimum solution is somewhere near the point -4, -12. And if you look at model B, just underneath, still on page 334, our objective function is n equals 3x minus 2y. And notice that we will subtract y. Okay, so instead of adding like we were seeing before, we're going to subtract this time if we were looking for or if we were verifying our points. And if we look at the triangle, the points, and again they're given in the variables x, y, are 0, 9, 5, 4, and 0, 4. And if you look at the triangle, so it's like that, and then it's the whole number coordinates. So my stippling won't be perfect, but it'll be something like that. And so you'll notice that here's our points, 0, 9, 5, 4, and 0, 4. None of them are included, okay? So not included. None of the vertices are included. Then we look for our minimum and our maximum. And here 0, 9 will be our minimum. 5, 4 will be our maximum. And again, neither are included. So for our solutions, we would say near 5, 4 will give the maximum solution. I'll separate that a little bit. And then near 0, 9 will give the minimum solution. And because these are whole number coordinates, you'll notice that that's given in the restrictions, and then also it's stippled. You'd have to choose the nearest whole number coordinate to test the points to find the minimum and the maximum solution. So you can practice this in the textbook with these questions. I am going to post another short video, so there'll be 2 videos this week. And make sure that you're working on the worksheets 6.1, 6.2, and real world problems if you haven't already handed them in.